Alternating current and voltage. In this video, we will study the basic principles of alternating current and voltage. We're going to start off with the sine wave. All right. Most of us will be familiar with the sine wave. If I graph the sine wave, okay, put in an axis, x and y axis, right? Sine wave would start off here at 0, goes to a maximum, back to the 0, and back. Of course, my drawing is a rough drawing and it's not symmetrical, right? But you get the idea. Right, so that's a sine wave. It starts off at 0 degrees. Sine of 0 is 0. Approximately here is 90 degrees. Sine of 90 is 1. Back here, 180 degrees. Sine of 180 would be 0. The sine of 270 would be -1. And back to 360 or 0. The sine of 360 or 0 would be 0. Okay? All right. Now, so we've looked at a bit quickly what is the sine wave. How about frequency? The frequency tells you how many cycles of the waveform is produced every second. All right. So, in a country like Barbados, our frequency of our mains is 50 cycles per second or 50 hertz. In the US, it is 60 cycles per second or 60 hertz. Countries like the UK, they operate on 50 cycles. All right. So this means that if we were to plot, if we were to sketch, give a graph over a period of 1 second, right, we would get 50 cycles. 50 cycles in that second. So, and the frequency would be 50 cycles per second, or it is given as 50 hertz. Okay, so that's the frequency. So let's move on. Period. What is the period? Period is a time, the duration of one period. Sorry, of one cycle. So it is the time from a beginning point to another beginning point. Okay? Right. Or if we had, for instance, if we had another waveform like that, the period would be, you can measure the period between two peaks. That would be also the period. All right? Or these two peaks, these two troughs here would also be period. So once you take similar points, the distance between those two similar points in the waveform would be called the time between those two similar points is called a period. So a period is given with the letter T. By the way, frequency is given the letter F. Right? Now, there's a connection between the period and the frequency. And the period is simply 1 divided by the frequency. So if you have, in our case, let's say 50 hertz for 50 hertz, the period T equals to 1 divided by F equals 1 over 50 equals 0.02 seconds or 20 milliseconds. Okay? Now, so we've covered period, sine, we look at the sine wave, frequency, the period. Next, wavelength. Now, wavelength is not very important for electrical engineers when we are considering 50 hertz, very low frequency, right? Because wavelengths are very, very, very long. The wavelength is the distance between, the actual distance in meters between two similar points. But it can be shown by calculation that the wavelength of a 50 hertz or 60 hertz cycle is very, very long, thousands of meters long. So it's not relevant at this point. But if you go into frequencies like cell phone frequencies of like let's say 300 megahertz or gigahertz, I don't know, let's say 20 gigahertz, megahertz, then wavelength becomes important because wavelengths are then very, very, very short, right? But nevertheless, just for completeness, I'll give you the formula for wavelength. Wavelength is connected to the velocity. So the velocity of a wave is equal to the frequency times its wavelength, right? That's the symbol for a wavelength. And the velocity we are talking about is the velocity of light, right? All electromagnetic waves operate at the speed of light, and that speed of light is v is equals to 3.0 times 10 to the 8 meters per second. So that's the speed of light. All right. So if you had to calculate the wavelength of say of 50 hertz, so we would say wavelengths. So since v velocity is equals to frequency times wavelength, you know that wavelength will be equals to velocity divided by frequency, and that would be in this case 3.0 times 10 to the 8 divided by 50, right? 3.0 times 10 to the 8 divided by 50, and that comes out at 6 by 10 to the 6 meters, which is 6,000 kilometers. Right? So you can see that's not really relevant. Now, but if we're talking about, let's go up here. Let's say we're talking about a frequency of let's say 20 gigahertz, right? A gigahertz is 10 to the 9. We can say that the wavelength will be equals to 3.0 times 10 to the 8 divided by 20 times 10 to the 9, and that comes out, sorry, 10 to the 9. That comes out, so that's 3 exponential 8 divided by 20 exponential 9, and that comes out to 0. That works out at 0.015 meters, right? Which is really 1.5 centimeters. So very short. So that's why, for instance, you have a cell phone. There's actually an antenna inside that cell phone, which is very, very short, right? So when you're dealing with very high frequencies, the wavelength is very short. But for our purposes, we don't have to worry about wavelength when we're dealing with lower frequencies like 50, 60 hertz, or even 400 hertz. All right. Okay, so we've covered what the sine wave is, what is we talked about its frequency, its period, and the wavelength. We will now look at some sine wave values. Okay, so I'm going to draw the sine wave again. Right now, where is the peak? The peak is at this point. Okay, right. So we know the peak is the highest point on the sine wave, right? Let's work our way from the bottom and let's look at RMS. This would have been dealt with earlier in your studies when you did rectifiers. RMS. Okay, and the best way for me to show you this is to give you an actual value. So let's say the mains value of a supply is 120 volts. If I tell you the mains value is 120 volts, by implication, we mean RMS. That's the root mean squared. Okay? Right. Now, how do we get the peak? Remember that peak voltage is equal to RMS divided by 0.707. In the case of a 120 volts, so the peak will be equal to 120 volts divided by 0.707. So 120 divided by 0.707 gives 169.7. 169.7 volts, approximately 170 volts to three significant figures. Okay? So that's the peak. Right. And we've talked about the RMS. Right. Now, what is the average? Now the average is taken over the entire period of the waveform. So we will have to take those values, add them all up together, take these values, add them all up together, and then take the average. But if you look at the sine wave, you will see that this side, if it's drawn symmetrically, my drawing is poor, so you can't see it here, but these values, positive values, will be equal to the negative values. So if you have positive values are the same and negative values are the same, they add to 0. So the average of a sine wave, so the average of your sine wave is 0. So that doesn't really help us, because let's say we were drawing power from the mains, right? We know that that voltage can do work, cause current to flow and then produce energy in the form of heat or motion. So something's happening. So to say that it is 0, the average over the period is 0, would not be useful to us, right? So we have to find another means of defining the voltage, and that's where the RMS came in. Now, we have simply told you how to calculate the relationship between the RMS and the peak. But what is the RMS? RMS, to get the RMS, this is what happens. You take these values here, which are positive, right? That's fine, and you square them, right? And you will get some values that are very large. So this will be the squared values. You take these values that are negative and you square them also. But when you square a negative value, you get positive values. So you end up getting values that are, again, very large in the positives. But you've actually transformed the negative peak into positive peak, right? But they are squares. Then you take the average, right? So you divide them up in strips. Take the average, and once you've taken the average, you take the square root to get back a meaningful value. Because if you had just left the average of these squared values, the value will be very, very large. So you then after you take the average, you take the square root. So basically, this is what you're doing. You get the root, the mean, and the square. Working backwards, you square first, so you square. You square. Then you take the mean, and then you take the square root. So you see you get the root mean squared. So that's where root mean squared comes from. RMS. It's the root of the mean of the squared values. And that is done so that you can get a meaningful value. Because if you took the average value, you would get 0. Okay? Now, we finally have to look at what's the instantaneous. The instantaneous value is simply the value of the sine wave. Okay, let me clear away some stuff. Okay, I'm going to clear away to start fresh so we can start with a clean board. Right. Right, so let's look at this. So we want to talk what's the instantaneous. So if we draw a line, right? And let's say this is our starting point, is 0. Right? We may want to find out what is the voltage at this point. Right? Which would be here. Or what's the voltage at this point? These values are all what we call the instantaneous values. Right? What is the value at a particular instant? That is why it's called the instantaneous value. All right? All right, so we have seen then, in the next slide, we're going to actually show you the equations that define the instantaneous value. All right? Okay. All right, so let's move on. So the sine wave equation. We're going to look at the equations for the voltage and also the current. You will see here, looking at it quickly, that they're similar, except that one is voltage and one is current. Right. So the instantaneous voltage equation, V, that's a lowercase v, is equals to the maximum voltage multiplied by the sine of omega t, and we'll explain that, plus phi. Right? Now, the Vmax is simply the peak voltage. Omega is it tells you how fast the waveform is changing, which is linked to the frequency. So the higher the frequency, the higher is omega. T is the time, and phi is what we call the phase angle. Right? So for instance, if you have more than one, or let me draw this quickly. Suppose we have two waveforms. So we can have, right, starting point. This could, let's say this waveform could be all voltage. And then we may have another waveform. Right? Another waveform that may be our current. You can see that at the starting point, this waveform is already at its peak, whereas this waveform, and the one in red, is now starting out. So we actually say that the waveform I, the current waveform, is actually leading, right? Is leading this voltage waveform by a certain amount, right? And this angle here tells you, right? Right? Or in case of the current here, this angle tells you, if we assume, for instance, that the voltage angle is 0, starts at 0, so that means there's the phase angle is 0, the reference point is 0, the current one would have an angle that is leading. And well, this is we'll see. This is approximately 90 degrees, but don't worry about that right now. It is leading. So this figure here tells you how much, right? So this is the angle. This is an angle. Now in maths, things have to be consistent. You cannot add apples and oranges. So if this is the angle here, this WT must also be an angle. Okay? All right? So if WT is an angle, omega we're just doing it roughly right now. Omega would have to be equivalent, would have to be an angle per time. That when you multiply it by a t, you get an angle. All right, well, we're going to discuss what omega is, and you can see that it's an angle actually in a form called radians. But just to make sure that you understand is that we're taking the sine of an angle. The phase angle, this here, this is an angle. Therefore, omega t has to be an angle. Therefore, omega has to be, and since this is t, omega has to be an angle per time. So angle per time multiplied by time give you an angle. All right. All right. So just let's clarify this again. So, well, we state that the equation for a sine wave, the instantaneous value for a voltage sine wave is V, the instantaneous value, is equal to the maximum value multiplied by the sine of omega t plus phi, where omega is the angular, is called the angular velocity, t is time, and phi is the phase angle. So similarly, the instantaneous value of current I is the maximum current multiplied by sine omega t plus phi. All right. So I hope that is quite clear to you. These are equations that you need to understand and commit to memory. Okay, now let's talk about radian measure. I just indicated to you that the angle, the speed of the rotation, the angular velocity is measured in radians. All right. So the question is, what is a radian? Now let's look at this by considering what we call a rotating phasor. A rotating phasor. Right. So we're going to draw. Let's draw a circle. Just draw the center. Right. And we're gonna have this as a horizontal line, and we're going to start. It's conventional to start our zero angle at this point. So the angle is 0, and we actually increase our angle by rotating anti-clockwise. That's by convention. We always rotate anti-clockwise. So when we start at this point, we have an angle of 0, and then we increase our angle. Let's say 30 degrees. Let's say maybe 45 degrees, let's say 60 degrees. And then when we come up here, of course, you know that that is a right angle. That's 90 degrees. You come across all the way across, you get 180. Down here, you get 270. And back here, you get 360 or 0 degrees. Okay? So consider a line of the length of radius that is rotating, right? And that is useful because when we are generating AC is generated physically by a rotating piece of equipment. Like in the electrical company, there are generators that are rotating, and they produce the AC waveform, right? So we describe it as in terms of mathematically as a rotating phasor, right? One complete rotation, one complete rotation of a phasor is 360 degrees, right? And 360 degrees equals 2 pi radians, okay? Where pi is equal to 22 over 7, or 3.142 to 3 decimal places, right? So right around the circle, 360 degrees, or 2 pi in radians, 2 pi radians. So if 360 degrees is 2 pi radians, then 1 radian is 360 degrees divided by 2 pi, which is 57.3 degrees approximately. So 1 radian is 57.3 degrees. All right? Now, how do we define the radian? or what is the radian, right? I'll give you the definition and then I'll explain to you what the radian is. The definition of the radian. The radian is that angle at the center of a circle subtended, right? A fancy word for like supported or hanging from an arc that is equal to the length of the radius of that circle. Now this is a mouthful, but it's best to explain it. So I'll say it again. The radian is that angle at the center of a circle subtended by an arc that is equal to the length of the radius of that circle. All right, so let me draw my circle again. So let me clear this one over here. Let's start fresh. Let's draw a circle. I hope I can draw a nice circle this time around. Try my best. All right, not the best, but right. Okay. All right, let me try a little bit better. All right, still having challenges with the pen. All right, anyhow, let's try. Okay, so what is a radian? Now, if you take a radius, which is that length from here, right? And you just stretch a string that length and take that string and bend it around, right? So you take that string and you bend it around here, the length of the radius, the angle formed by that arc that is the length of a radius is called 1 radian. Okay, so that is what a radian is the angle. It's the angle that is created when you take an arc that is the length of a radius. That angle is called a radian. So the question is, how many of these radians? So that's another one there, another radian, and another radian. How many of these can you get around the circle? No. If the distance around a circle is 2 pi r. The circumference of a circle is 2 pi r. Okay? So if a radian is produced by a radius, you just need to find out how many of these are around there. So you simply divide the 2 pi r by r, and that will cancel out, and that will give you 2 pi radians. So there are 2. So you see it here? There are 2 pi radians in a complete circle that is 360 degrees. Okay? All right. So I hope that is clear. So when we are doing these calculations in AC theory, we are going to be using the radians rather than degrees. All right? We're going to be using the radians rather than degrees. Okay. Right. So let's have some fun here now. What we're going to do, we're going to try to plot the sine wave based on a rotating vector. All right. Now this diagram is not perfect, so you will not get a perfect sine wave, but it will suffice to illustrate. So let's say we're going to start here. All right. So let's say this is our starting point, and let's say that this is our axis along here. Okay, that's our y-axis, and along here is our x-axis or time or angles in radians. Okay? Right. Now, when we start off at 0, with the phasor at this point, you get 0. With the phasor move up here, let's say in this time interval here, we're now here. Another time interval, we're now here. Another time interval, we're now here. Another time interval, we're now here. And then we get to the peak, we're now here. So you see that you get a waveform that goes up, and then you're going to come back down. Okay? Over here now, when we're over here, we're going to be here. Right? So we put it at point. When we're over here, we're going to be here. When we're over here, we're going to be here. When we are over here, we are now going to be here. So now we can come back. We can come back down. Ooh, sorry. All right. Let me take that out. Right. Good. And similarly, as you continue, you would go round and round, and you go, oops, round. Yeah. So you come down, and you go down to your, and then you go back up, and then you're off the scale. All right. So that is how you would generate a sine wave from a rotating phasor. So the phasor is going to start here, and then it's going to go here, and it's going to come here, and it's going to come here, going to come here, then it's going to be at the top, and it's going to rotate all the way. Always remember rotating in an anti-clockwise direction. All right. Let's look at some points at the top here. That's halfway here. Remember, if you're talking in radians, a complete waveform will be 0 all the way down to 2 pi. Half of 2 pi will be pi, right? So from here, from 0 back to 0 will be pi. From here up to the peak will be pi on 2. And, if you want to talk about degrees, we know that is pi on 2. Right? Okay, pi will be 180 degrees. Pi on 2 will be 90 degrees. Right? Pi on 4 will be 45 degrees. Okay? Right? But I don't want to get into the habit of mentioning degrees right now. Just show you the relationship. We're going to stick with using pi. All right? Oh, and by the way, whenever you're using pi on your calculator, you have to make sure that your calculator is actually on on radians. So let me say that again. When you're dealing with radians, you must always make sure that your calculator is on radians. Right? And not degrees. If not, you're going to get totally incorrect answers. All right. So I hope this helps. All right. So let us move on now. We have looked at the sine wave. Let's look at the square wave. So the question should be, well, you may ask the question, why a square wave? What is the importance of a square wave? Now, a square wave is very important when it comes to industrial controls, like controlling the speed of a DC motor, right? And I'll explain later on. I'll explain the application of controlling the speed of a DC motor via a square wave. All right. So what I'm going to do now, I'm going to draw you a square wave, and then we're going to discuss all of these concepts, these terms: the frequency, the period, the amplitude, the pulse width, the mark to space ratio, pulse width, modulation, and average value. Okay, so let's draw our. Ooh, so I don't like that line. So let me erase that line. Okay. So let me try to draw a straighter line. That's much better. Okay, so I'm going to draw here now a square wave. So square wave starts at 0, goes up to a point, goes back down, stays down. In this case, we're going to make it stay down as long as it was up. So that's our square wave. All right. Good. Right. So let's assume, just to show you a bit about this, let's say that our voltage was here 24 volts at the peak. Right? Right. Let's use that as our voltage, and to discuss what happens to the square wave. Now, if we assume that the pulse is on as long as it is off, we're saying that this has a mark to mark to space ratio of 1 to 1. Okay, mark to space ratio. The mark is at the top and the space is at the bottom. Right? We could have a case where we can have the waveform on for a short period of time, right? And off, and then back on, off, sorry, on, right? So let's say in this case we have a mark to space ratio. Maybe this is on, let's say roughly it's not quite, but let's say this might be 1 and 1 space between there, and this space is 5 between here. So mark to space ratio will be 1 to 5. Okay? All right. Now you'll see where this comes in later on when we talk about pulse width modulation. Actually, pulse width modulation is a means of changing the mark to space ratio. But what is the purpose of pulse width modulation? And we're going to see that as I give you an example of controlling a DC motor. All right, so let's go through these terms now. So frequency, the frequency is the same as, it's discussed in the same way as the sine wave, right? The frequency is how many complete cycles. And a complete cycle here will be from here, this starting point back to this starting point, all the similar points. So here we were going up. So we can't say this is a similar point. The other similar point will be here, where we're also going up, right? So the question is, how many of these complete cycles from here to here do we get in 1 second? And that will give us the frequency. So the number of cycles per second. Now the period is again from one similar point. So the period T will be from there to this point here, right? Or if you want to say it from here to another similar point coming down, when that's coming down will be here. So that would also be a period. All right. Okay, so that's the period. So we've done with frequency. We look at the period. The amplitude is simply the maximum value of the maximum height of the waveform. That's the amplitude. The pulse width is simply the width of this of the pulse, right? So that's the pulse width. As I mentioned already, mark to space ratio is the ratio of the pulse, right, where the voltage is on to when it is off, right? Now, pulse width modulation, as I mentioned, is a means of changing the mark to space ratio, right? And we're going to see how that will affect the average value. Now, let me give you an example. Let's say we had to calculate the average value of this waveform here. The average value of this waveform. Apologize for that pause. What is the average value? To find the average, what we would do, we would divide up the number of strips. Okay, it's 1, 2, 3, 4, 5 strips. We would divide the space in the same number of strips, 5. Right? So what we would simply do to take the average, we would say we have a 24 volts here. We have another 24 volts here. We have another 24 volts, another 24 volts. We have another 24 volts. So we have 5 of those. And then we have 5 zeros. 1, 2, 3, 4, 5. Add them all up together, right? So you get that is 24. 5 times would be 120 volts. All zeros would be 0, and the total would be 120. But how many intervals do we have? We have 10 intervals, right? We have 10 intervals. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 10 intervals. So the average will be then 120 divided by 10, which equals to 12 volts. So the average of a 24 volt amplitude square wave that has a marked space ratio of 1 to 1, the average value will be 12 volts. So here's where motor control comes in. Suppose we have a motor that we've designed it to run at 24 volts maximum speed, right? If you switch on the power supply, on all the time for 24 volts, it's going to run at full speed. But if you switch on the power supply on for as long on as off, and we pulse it, we're going to get, in this case, an average of 12 volts. So the average is going to actually come down as 12 volts. So the motor is going to run at a slower speed. Okay? If you want to make the speed variable, we just have to vary the mark to space ratio. Right? If you want 3/4 of the speed, we may just have to do it like this. Come off. So we have all that on, off for a little while, on. Right? So we've now changed the mark to space ratio where we have it on, let's say, for 3 times as long as it's off. Right? Okay? And that would give us a 75%. You know, 3 to 1. Right? It would be on. This would be like 75% and 25%. Right? 325 is 75, 125 is 25. So if we do that, if you have a marked space ratio of 3 to 1, we're gonna actually work. If we were to work it out, you would get, instead of 24 volts, 24 multiplied by 0.75, which should come out to 18 volts. So you're gonna run, instead of running the motor at 24 volts, you're gonna run at 18 volts, which is 3/4 of the maximum voltage. So this is where pulse width modulation comes in. It's very useful in industrial controls where you want to control the speed of a motor via a computer or PLC or whatever that can actually modulate pulse width, modulate the waveform. All right. So pulse width modulation, and we've talked about the average value. All right. So I hope this helps. So to recap, we know the frequency. The frequency is how many cycles per second. The period is the length of time for a complete cycle. And remember that period T is equals to 1 divided by the frequency. Okay? We know what the amplitude is. Pulse width, length of the pulse, marked space ratio, how much is on to how much is off. Pulse width modulation, the changing of the marked space ratio, and of course the average value depending upon the marked space ratio. All right, so I hope you gain from this video on alternating current and voltage. All right, thank you for watching.